to draw a quick cross-section conceptually and sort of walk through what we've been driving through for the past 2.5 hours, 3 hours now. So, start out here. Here's the Gulf of Mexico. Out here in the ocean. And we start where we are in Houston, and it's pretty flat. It's all dirt. There's not a lot of rock sticking out of the ground, so we have to drive north. But a key thing to consider is that all of the sediments that we're standing on in Houston sort of dip shallowly out into the Gulf of Mexico. And then they dip back up northwest, or northwest, towards central Texas. And so here we are in Houston. And if you looked at your packets that we gave you, and if you look at the geologic map of Texas, what you'll notice is that as you get farther and farther from Houston, you get different color bands of rocks. And those rocks, or the sediments, are getting progressively older as we move up towards Austin. So as we go up, driving northwest, pretty much all of the strata are dipping very gently out towards the Gulf of Mexico. And we're getting from very young material sediments. So out here in Houston, we're in what are quaternary deposits, so sediments that have been deposited in the past 1,000,000 years or so. And then as we move further towards Austin, so here we are up here in Austin, across the buildings, we're getting farther and farther back through time in terms of what the rocks are underneath us. So here we move into Miocene age rocks, so stuff that's about 20 million years old, and then Oligocene age rocks, so about 35 million years old, and then up into Eocene age rocks. So you have this sort of gentle, steady progression of older and older stuff. And one of the things to note is that you start off here in Houston where everything is very flat, and then as we get further and further towards central Texas, you sort of have slightly hillier country. There's a little bit more topography. And then a really important thing happens once you hit Austin, and we're standing on it. So you noticed when we were coming up, we've increased elevation significantly. Downtown Austin is sort of over there, but it's below us by a significant amount. And so there's this relatively large topographic step, and then you get up into a very different area geographically that's known as the Edwards Plateau. So up here we've got a higher area called the Edwards Plateau. And now we actually start getting rocks exposed at the surface, real rocks, rather than just really weathered stuff out here. And this jump in elevation is called the Balcones Escarpment. And it pretty much runs all the way along Texas. It's sort of an arcuate shape. So if this is Austin, this is Houston, there's this big topographic step. It's got this shape to it. And you basically go from the sort of Gulf of Mexico terrain to the what's called Edwards Plateau. So that's the Balcones Escarpment. And what's controlling this topographic feature is a large normal fault system. So there's actually a fault between us and downtown Houston, cutting through the earth. It's a normal fault, so we're in the footwall, which has gone up relative to Austin, and the hanging wall has gone down. And up here where we're standing, we're on these nice, layered, beautifully exposed carbonates, or limestones, of what's called the Edwards Formation. this all throughout the area where we're driving around today. It's pretty much exposed everywhere along the Edwards Plateau. And this same limestone is down here somewhere in the subsurface underneath Austin, and then continues off towards the Gulf of Mexico. We'll give it a little brick pattern like geologists like to do. So again, this normal fault has brought this limestone up towards the surface. It's exposed. We have this big topographic break right here in central Texas, and then all the stratigraphy and other rocks that we see today are much deeper underneath the ground as we move back towards Houston. So that's sort of a general overview of what we've driven through and what we're about to enter in terms of the physiography and some of the ages of the geologic units. Again, the rocks are not very well exposed at the surface, but we've got tons of data from wells that have been drilled into the ground in terms of what that stratigraphy is, either oil wells or gas wells or simply water wells that have been drilled into the area. So keep this structural relationship in mind. We'll come back to it a little bit further towards the end of this stop when we look at some of the other interesting features. So now what we're going to do is we're going to walk out onto some actual outcrops so we can actually see rocks, and we'll start looking at those. What kind of rocks are we dealing with here, do you think? Well, we got three main types. We've got igneous, metamorphic, and sedimentary. What are we looking at here? Who thinks metamorphic? Raise your hand. Okay, that's good. Who thinks these are igneous rocks? Anyone? Okay, good. Who thinks they're sedimentary? Okay, good. You're all passing the test so far. So, we use some beautifully exposed sedimentary rocks. It's good if you sort of turn around and take in their grandeur, their spectacle. On the other side of the road, we have a nice, beautiful view of them. And what you can really nicely see on this road cut here is one of the primary features we look at for people to see in sedimentary rocks, and that is bedding. So we talked about the structural features of sedimentary rocks. The key thing is the individual layers of sediment that are deposited over time, these beds of sediment. So you can see over there this beautiful horizontal layering that goes straight across all the way. You can follow single beds of variable thickness all the way from the south end here, all the way straight across to the other side. So very continuous and very nicely exposed here. And you can also see that there's a lot of variability in that bedding, right? There's some layers that are really thick, and some that look like they're much thinner. And then if you look above, sort of at the upper wall, you can see that there's a lot of variability in terms of how those layers erode as well. So some of them are much stronger, forming little ledges that stick out, and some of the layers are much weaker and are being sort of eroded away at a much higher rate. So you get little heat sets of this topography there. So there we have, this is bedding. Now you all have seen it firsthand, seen the test. And the formation that we're dealing with here is called, as I said over there, called Edwards limestone. So again, what kind of sedimentary rock is a limestone? Is it a detrital rock or a chemical sedimentary rock? Who thinks detrital? Okay, who thinks chemical? A lot of undecided people here. That's okay. Right, so carbonate rocks are chemically precipitated rocks. So we're looking at material, calcium carbonate that precipitated out of the water. And the Edwards limestone is actually a pretty dirty carbonate. So there's a lot of clay particles in it as well. So there's a pretty good detrital component in these sediments in addition to the stuff that precipitated out of the water. So the Edwards limestone is, again, interesting in that it's exposed all throughout central Texas. It's exposed here, everywhere we'll be driving today, and then you even find it way out in Big Bend National Park. And then, again, as you move towards Houston, it's there. It's just underneath all the other sediment that was come after it, piled on top of it. So it's a pretty extensive formation. So what sort of environments do you get carbonates in? Is this a lake environment, or do you think this is a marine environment? Who thinks lake? Okay, you can get carbonates, but yes, this is not a lake. Who thinks a marine environment? I think it's two choices here. So if you didn't raise your hand before, you should be putting it up now. Right, so these are marine limestones or carbonates. And one of the neat things about this location is that there's actually a fair number of fossils in here too. So why don't you guys spend about 10 or 15 minutes digging around the rocks in here. There's some nice exposures up here on the ledge. Just be careful, it's a bit slippery. And just sort of see what fossils you can find. So here's a little block here that's got some fossils, and you can usually tell what they are because, first of all, they look like a shell, which many of us are familiar with, and also they tend to be sort of more of a khaki color rather than the light gray of the limestone itself. So why don't you go through, take a look at these fossils, and you should be able to identify some of the critters in here, at least to a first order. So why don't you spend some time, there's some really beautiful fossils in here. So if you get lucky, you can find a nice one to bring home and put on your bookshelf. You can walk up the little slope here again, just be very careful, it's slippery. There's plenty of exposure down here, chunks of rock and fossils, so don't feel that you have to go climbing up the hill. Anybody able to identify anything specific in terms of species of organism that you can find in these rocks? Well, that's not very specific. Anybody find something that they can identify? A lot of them look like this when I'm holding in my hand. I'm sure you all can see this very clearly. Oysters! Oysters! Exactly! Give the man a bonus point. So there's a lot of oysters in these rocks. So what sort of environment do you find oysters in? Where you go? We can find them right in the Gulf Coast. Where are you going to go if you want to gather some oysters? Shallow marine areas. Back Bay of Galveston, good place to find oysters, although you wouldn't want to eat those necessarily. But yeah, shallow, very shallow marine environments. So estuarine environments, back bays, things like that. So we're dealing with a very shallow ocean in which these rocks are being deposited. You can tell that from the organisms that are moving out. So the Edwards limestone, someone was asking about the age of these rocks. The Edwards limestone is about 100 to 105 million years old. So we're talking about a long time ago. What was running around 100 million years ago? Dinosaurs, right. So we're talking about the Cretaceous period where you got a lot of cool dinosaurs running around. And this was part of what's called the North American Interior Seaway, or the Cretaceous Interior Seaway. So at this time, there was actually a shallow ocean. Ocean levels were a little bit higher, and there were some other things that were going on. So there was a continuous shallow ocean all the way from the Gulf of Mexico to Hudson Bay in Canada. So one of the things I want you to do is turn around for a second and look at the outcrop behind you of this Edwards limestone. And what you can pay particular attention to is sort of at the ends of these outcrops, where the outcrops intersect the side of it. So we get a change in color, right? And you can see it on the other side as well. As you get towards the edge of the outcrops, there's all this nice fresh stuff that was blasted away when they put the road through. And then as you get closer and closer to where the actual surface of the Earth was, more of a past several thousand years or more, you get a more of a sort of a khaki color, right? A nice beigeish, brownish something. I guess someone who's more into color can get more accurate description. But anyway, what do you think is going on there? What's happening? What's causing that difference in color as you get towards the surface? Vegetation, okay. What would the vegetation be causing potentially?
Acidity.
Okay, so maybe interaction with more acidic waters. So what you're looking at is chemical weathering or weathering interactions with the Edwards limestone. So down where we were, it's nice and pristine because it was several hundred feet from the surface for a long time. And then as you get towards the edges where you're starting to interact more with surface water, vegetation, water that can actually seep into the rock, you start getting some discoloration, which is from weathering. And so up here at the top, you see something that's very characteristic of the Edwards limestone, which is right up here. Up there. So that's naturally weathered out holes in the rock, or caves. And so the Edwards limestone is what's often referred to as a cavernous limestone, in that you often get these very large cavities that are weathered out of it as water seeps through the rock. So again, we're dealing with a carbonate, something that's relatively easily dissolved, as long as you've got a little bit of acidity in your water, which most water has. And so over millions of years, you erode these little cavities in the rock. And that's good in many ways in that it allows water to move much more rapidly into and through these rocks. So the Edwards limestone is this cavernous limestone. It's very good, what's referred to as an aquifer. It's a rock body that can store and transmit water very effectively. And so this formation is something that a lot of people are interested in tapping into as a groundwater source for agriculture, industrial, municipal needs, whatever. And so the Edwards limestone that's underneath Austin and much of the local region is an important groundwater source, and it's referred to as the Edwards Aquifer. So down here is the Edwards Aquifer. Now, a critical thing about these groundwater source resources, these aquifers, is we need some way to get water down into the ground, into these rocks. Because if we just extract water and we can't get new water in, we'll very rapidly deplete them. So we need what's referred to as a recharge zone, or an area where the rainwater can get back down into the ground and fill this reservoir back up. And that's what this normal fault system, this Balcones normal fault system, allows for. So rainwater can come in and trickle down through this fault zone, because you've got a lot of broken up fractured rocks where they've been faulted, and then it can flow back into this aquifer and fill it back up again. So as we're driving out, you'll notice signs that say you're now entering the Edwards recharge zone and then exiting it, because these are incredibly environmentally sensitive areas. You don't want to be dumping toxic waste in the only area that water seeps back into these groundwater reservoirs. Again, these are critical for municipal water needs as well as agriculture and industry. So they're very sensitive zones. So again, this normal fault system is where water gets back into this critical resource area. Alright, so right here what we actually have exposed is one small fault associated with this Balcones normal fault system that you can see. So if we're looking up here at this outcrop, what we can see is there's sort of a nice big thick resistant bed up there that, as you follow it along the outcrop, actually drops down a little bit. So there's that formation right there. The bed comes along, and then if you go over to there, that bed has been dropped down by about maybe a foot. And so you can actually see the fault, the fracture that's accommodated that motion right in there. So there's a break in the rock. You can see where pieces have fallen away. That's one of these normal faults. The other thing that you can see there is on that surface, you can actually see the fault surface itself, not there. Yeah, right in there. Just to the left of where I hit. You'll see that fault, that planar surface has these linear features that go up and down on that rock face. And those are referred to as fault striae. So they're actually from when that fault moved, the two sides on either side of that fracture scrape against each other and basically end up sort of dragging grooves into the opposite block as they slide past each other. So these are very useful, and then they tell us exactly which way that fault actually moved. Some faults like to move up and down, normal faults and reverse faults. Some like to move side to side, strike slip faults, and then a lot of faults usually have some oblique component. But for these striae, we can see that they're mostly straight up and down, so we're just talking about normal displacement. And again, this is a very small fault, but it's related to this much bigger Balcones normal fault system. And again, it's dropped all of the rocks that we're seeing up here, several hundred feet underneath Austin today, downtown Austin, and is responsible for this topographic break and the very different physiography that we have to the northwest as we get up into the hill country rather than off to the southeast. All right, so again, nice little normal fault. See these striae, and the other, of course, thing we just talked about is these faults are what allow water to get into this critical aquifer system underneath the greater Austin region. All right, so again, when we're driving out, make sure you look for those signs at about a mile, then 2 miles down this road before we turn back onto the 71. And then just these big green signs saying Edwards Aquifer Recharge Zone, environmentally sensitive area. And they say you're now entering, and then they say you are now leaving. So just keep an eye out for those signs.